Hello everyone, welcome to my YouTube channel. In this video, I'm going to cover how to manage and securely roll out your application secrets in a Kubernetes cluster and OpenShift clusters. At the end of this tutorial, we'll have some basic understanding of main concept of Hashicorp Vault, how does it work, what problem Hashicorp Vault trying to resolve, and how we can use external secret operator to integrate with Hashicorp Vault and create Kubernetes secret inside the Kubernetes cluster. Let's quickly go through the topic which I will cover in this course. We will start with basic concept of what is secrets, what is Kubernetes secrets, and why we need to secure those secrets. After that, I will talk about what is Hashicorp Vault and the basic concept of Hashicorp Vault and what problem Hashicorp Vault trying to resolve. And then we will move into next topic, external secret operator. What is external secret operator and what problem external secret operator trying to resolve? How external secret operator integrate with Vault to securely create Kubernetes secrets. Finally, I will do demonstration of each concept and conclude this video. For the demonstration, I have created this blog post called Manage Secrets in OpenShift using Vault and External Secrets. What is secret? In technology, a secret is something you wish to keep hidden from the general public. Simply said, it's data that should not be visible to your codebase commit and history, but is essential for your app to work properly. It's a data that can be used to authenticate one component to another and or identify and trust a foreign object. It can be a database password, PayPal token, certificates, SSH keys, GitHub token, and many more. Because of the sensitive nature of secrets, there are various challenges associated with secret management. Some of the challenges are understanding where all secrets exist, who has the potential access to secrets, who has used the secrets and when they use it, how to securely roll out secrets so that application can consume them without being exposed to an unauthorized user, how to frequently rotate secrets, revoke access if required, and many more. Now we understand what is secrets and what are the challenges associated with the secrets. The question is how we can resolve it. There are various tools and technology which is working in this area to solve this problem. Some of them are Hashicorp Vault, AWS Secret Manager, Achilles Vault, Azure Key Vault, Docker Secrets, Teleport, Authing, Score, Keywise, and others. Kubernetes secret is also a mechanism to help solve some of the challenges associated with secrets. Created secrets holds a small amount of application data such as passwords, token, key, and provide that data as an API object so that a container running as a part of pod can consume it. You can provide this data using environment variable as a volume mount. You can secure this data using RBAC permission, encrypt data using REST encryption and or SSD encryption so that you can transport those data over the distributed network securely. We now have basic understanding of secrets and Kubernetes. Let's go to the topic Vault. As per official definition, Vault is an identity-based secrets and encryption management system. There are some buzzwords here. Identity-based. Vault support various identity provider. You can use token and username / password based authentication. You can integrate with LDAP provider. It has support for JSON based web token JWT, auth services, and others. The next buzzword is secret management. Vault natively supports various secret engines. It has support for key value pair KV, PKI certificates, SSH keys. It can manage secrets for different cloud providers like AWS, Azure, Google Cloud, Ali Cloud, Active Directory, and it can automate secrets for different infrastructure like console, databases like MySQL, Postgres, Nomad, RabbitMQ, you name it, list is growing. The next buzzword is encryption management. Vault provides encryption service gated by authentication and authorization. If you look at the architecture diagram of Vault, there is a clear separation of components that are inside or outside of the security barrier. The storage component, which is outside of barrier, is untrusted and only serves the purpose of storing encrypted data. So even if database is compromised, attacker can only see the encrypted data. Anything which is inside the barrier requires authentication and authorization to decrypt the data. Now you have pretty good understanding of what is Vault. Let's explore some of the capabilities of the Vault. Apart from storing secret data, Vault can generate dynamic data. For example, it can generate and automate SSH key pair, certificate, database password, AWS authentication token, GitHub token, and others. And apart from providing data encryption, Vault can automate lease period for the secrets, auto renewal of the secrets, and revocation of the secrets. So far, we have covered secrets, Kubernetes secrets, and Vault. The final topic is external secret operator. Simply put, external secret operator ESO is a custom operator / controller which fetches the secret from the secret provider and create Kubernetes secrets in a particular namespace. Now the question is, do we need ESO to integrate with Vault? The short answer is you don't need it. You can create your own process or add functionality in your applications to fetch the secret from the Vault. In fact, ESO is very limited and has only support for Vault KV engine. So this may not be a right operator for your use case. But for our use case, this is satisfying the requirement and exactly what we need, no more, no less. So we're going to use it. We now have enough background to start the demo. Before we start, there are some prerequisites. We need a working OpenShift cluster with admin access where we can run this demo. If you don't have running OpenShift cluster, you can use code-ready containers CRC to set up OpenShift on your local machine for the testing. Take a look on this YouTube video which help you to move forward with CRC. The second prerequisite is you need Helm version 3 to deploy Helm chart for both Vault and external secrets operator. You can download Helm version 3 from official Helm page, where you can download binary releases directly and put it into your system path or through your package managers for your operating system. They have packages available for macOS where you can use Brew. For Windows, you can use Chocolatey. And for Debian, you can use apt-get. If you are using other operating system, they have package manager for other operating system as well. Now the third requirement is you need OC or kubectl client at kubeconfig file to interact with OpenShift cluster. You can download OC CLI from this official Red Hat page. They have packages available for supported operating system where you can download package for Windows, for macOS, Linux. You can also download OC CLI from OpenShift Web Console. And for kubectl, you can download binary from this official web page, where you can find package for supported operating system. Once you satisfy the prerequisite, you can start with the blog. Let's start with the Vault installation. Let's export kubeconfig file first so that you can run OC command, OC get nodes. This is a 3 nodes OpenShift hyperconverged cluster where all of the master nodes are also workers. I think I deployed Vault before. Let's get the pod from Vault namespace. There is nothing deployed in Vault namespace. Let's go back to the blog and copy this OC new project Vault command. This command will create a new OpenShift project as well as Kubernetes namespace called Vault. Since we already have Vault namespace, let's delete that first. And let's paste that OC new project Vault command from the blog. You can see from log here Vault project is created, which also creates Vault namespace. We also have some service account created. Let's go back to the blog. copy this helm repo add command, which allow us to add helm repository for Vault. Let's paste it. It come up with the message repo already exists because I already had that before. As you can see here, in your case you will see different messages. Helm repo search command display the latest stable version of the chart found in that public repository. Depending on when you are watching this video, you will probably see different version instead of 1.9.2 version of Vault. Let's move forward. Let's copy this YAML definition from the blog. Create a file called values-override.yaml. And paste the content we copied from the blog. Save it. Get the file so that we can analyze it. This Vault chart by default support installation on OpenShift cluster. The global.OpenShift value should be set to true for OpenShift cluster. UI.enable set this value to true if you want to enable UI. Once this service object is enabled, we can create OpenShift routes pointed to this service object to expose Vault UI outside of cluster. In this section, we are enabling Vault injector and pulling container image directly from Red Hat registry. Vault injector is a Kubernetes admission webhook that adds Vault agent containers to parse for consuming Vault secrets. We need persistent volume so that Vault can store secrets. For persistent storage, we are using this storage class called OCS-storage cluster-safefs. Use your own storage class here to create persistent storage. On the route section, we are creating OpenShift routes. This is how we expose application running inside OpenShift cluster. This is not mandatory for this POC, but if you want to expose Vault outside OpenShift cluster, you have to enable this. Image section contains Vault images, which is pointed to Red Hat registry. HA section enables Vault to run in HA mode. In HA mode, Vault will configure itself to use console for its storage backend. But in this case, we are using Vault integrated RAF storage. Unlike the typical HA modes where Vault persistent is external, such as console, enabling RAF mode will create persistent volume for Vault to store data according to the configuration under server.data storage. We're also creating 3 replicas of Vault, and since we have 3 nodes in this cluster, it will deploy Vault in its machine. Alright, let's go back to the blog and copy this Vault install command. Switch to Vault project if you are not already in the project. Paste the value. Here we are saying create Vault with name vault-server and use overrides from override-values.yaml file. Vault is deployed successfully. Let's validate with OC-get parts command. And you can see 3 instances of Vault are running. With 1 instance of Vault agent injector, let's add -override, and you can see Vault is deployed in each instance of OpenShift cluster. However, Vault is not initialized, and because of that, health check for Vault parts are failing. And you are seeing these 0x1 status in each Vault instances. Let's verify Vault service object, run also get svc. These are the service objects deployed in a Vault namespace. Now next, we are going to create OpenShift routes and point to this Vault service UI service object. We have only 1 route created by default with this default DNS record, which is pointed to Vault service active instance. Let's add routes for UI components also. Copy this YAML content from this blog and create a file with this content. Let's analyze this file. Here we're saying create a routes with name vault-console, which is pointed to Vault Server UI service object, and target port is HTTP. And DNS is this record. This is not mandatory, and if you skip this section, it will create the DNS with the same record. It's a default pattern for OpenShift, which always contains routes name, in this case vault-console, followed by dash and namespace, .apps, and followed by cluster-name and DNS record for that cluster. Let's apply this YAML definition. Route is present now, and we can access this URL from the browser. Alright, Vault UI is loading. Since Vault is not initialized and is sealed currently, you cannot do any operation on it. The Vault operator init command initializes a Vault server. After initialization, Vault's storage backend is prepared to receive data. Copy this command Vault operator init from the blog. Paste it. All Vault servers share the same storage backend, so you just have to initialize one Vault. During initialization, Vault generates an in-memory master key and applies some secret sharing algorithm to break that master key into a configured number of keys here, also called on-cell keys. By default, configured number is 5. You can actually override this value using keyshare argument during init process. Before we do any operation in Vault, we have to unsell the Vault. And for that, we have to regenerate the master key by applying those on-cell keys. By default, you need 3 on-cell keys to create master keys, but you can override these values to your preferred number. Init process also generate root token to authenticate with Vault. Let's save these keys so that we can use it for future operation. Create a file called vault-token.txt and paste the keys. Vault is initialized, but if you notice here, pods are still not ready to receive the traffic. Health check is still failing. As I said before, we have to unsell all the Vault instances using Vault operator unsell command and supply the 3 unsell keys one by one for each Vault instances. Let's copy the unsell keys from previous output. Apply it. Now you have to repeat the same process 2 more times with different unsell keys for Vault-server-0 instance. Here if you notice, Vault is still sealed and unsell progress for this Vault instance is 2 by 3. Let's apply different keys one more time. Finally, Vault status is false. And if you do also get parts, Vault-server-0 pod is up and running. Still 2 parts are not running, and let's fix that. Let's try to unsell Vault server 1 directly. You're seeing this error message, Vault is not initialized. And the reason behind this is the Vault Server 1 and Vault Server 2 are not part of the same Raft storage. Let's join the remaining parts to the Raft cluster and unsell them. Vault Server 1 is now part of the same Raft storage. Let's repeat the same process for Vault Server 2. Now all parts are part of the same Raft server, so let's start the unsell process. Unsell process for Vault Server 1. And unsell process for Vault Server 2. Finally, all Vault parts are up and running. To verify if the Raft cluster has successfully been initialized, we can log into the Vault using root token. List all the Raft peers using Vault operator Raft list peers command. As you can see, we have Vault Server 0 as leader and other remaining 2 servers are followers. Go back to the browser and access Vault UI again. You'll see this sign-in page where you can log into the Vault using different mechanism. It has support for username, OIDC, GitHub, LDAP, and many more. Of course, you have to configure this ahead of time to make it work. For now, we have root token which we can use to authenticate. Let's copy that root token from our vault token.txt file. Alright, you are authenticated successfully, and since this is the root token, you have authorized with admin permission. By default, only Copy Whole secret engine is enabled. Vault support various other secret engine which you can enable from here. For our next steps for external secret operator, we need this KB key value Vault engine. Let's just start with external secret operator installation. In blog, you will find external secret operator installation section where I documented this process. We are using Helm chart for this operator also. I already have Helm chart repository added for this operator. In your case, you use this command to add the repository. Create an OpenShift project called external secrets. This is not mandatory, and Helm can create the namespace. If you want to skip this step, you can do so. Next step is installation, so copy install command from the blog and paste it in your terminal. External secret operator is up and running now. Now we can integrate this operator with Vault provider. With the help of custom resource definition configuration called cluster secret store, create a file name called cluster-secret-store.yaml. Copy YAML content from the blog and paste it in that file. If you analyze this cluster secret store.yaml file, you'll see kind cluster secret store with API version external secret.io-v1 alpha 1. The name of this object is vault-backend, and we need this reference later for action secret object. We are using provider Vault. There are other providers this operator support, and Vault address is pointed to Kubernetes service object. Because both Vault server and external secret operator are running in the same OpenShift cluster, if they are running on a different cluster, you have to use DNS name which you can resolve from outside of this cluster. Vault.path is equals to secret, which is referring to key value KV secret engine, and it's the only secret engine external secret operator support at the time of this recording. Vault version is V1. As per official doc, you can also use V2. Auth is the authentication to integrate with Vault. There are different ways you can authenticate with Vault. For simplicity, let's use the Vault root token, which we generated as a part of the Vault initialization process before. Copy this Kubernetes secret YAML definition, create a YAML file with that contain on token section. We have to change this base64 encoded token reference. Create base64 text data using your root token. Copy this value and replace in the file. Let's apply this secret to the cluster in Vault namespace. Now we have to match this Vault token secret reference in cluster secret store YAML file. Apply cluster secret store.yaml definition to OCP cluster. Object created. Let's check the status of cluster store. And the status is valid, which means it's able to integrate with the Vault. The next step is creating external secrets. External secret object describe what data should be fetched from the Vault and how the data should be transformed and saved as Kubernetes secrets. Let me change the name of external secrets and target name, because I already have external secrets and target with that name. You don't have to do this. Let's analyze this file. This external secret object is referencing to Vault backend cluster secret store object. Secret store ref should match with cluster secret store name. This way operator knows from which provider it should fetch the secret and how to authenticate with that provider. Spec.target.name is the Kubernetes secret name you want to create. In this case, it's going to create pool secret -cluster -SNO02. The spec.data section defines the connection between the Kubernetes secret keys and the provider data. It's a list object and you can fetch data from multiple endpoints. In this case, we are saying get property Docker configuration from Vault endpoint secret /OpenShift pool secret and create Kubernetes secret with the key name .docker configuration with that Vault data. So far we don't have any secrets on Vault. And also key value KV secret engine is not enabled. Let's log into the Vault using root token. And enable that KV secret engine. We have only Vault secret engine at the moment. We can enable KV engine using vault enable dash path equals secret slash space KV command. KV engine is enabled. You can also verify that from UI. We don't have any data in that secret endpoint, and we're going to create the data in the next steps. It's possible to add secret data from UI, but I'm not going to use UI. Instead, I'm going to use CLI. Let's copy this command from blog. Paste it. Data written successfully. Which you can verify from UI also. We have data in Vault, but we don't have any external secret object which is fetching this data from Vault. Let's run OC-get-secrets command. We don't have any secrets with that name at the moment. Let's apply this external secret object which we created before. Object created, and run that get secrets command again. As you can see, a new secret is present with the following content. Where base64 decoded data matches Vault secrets content.